Dr. Shragi here, and I'm here to talk to you today about the carbon cycle. And in particular, we're going to be talking about the natural components of the carbon cycle, the ways in which the natural system picks up carbon and deposits carbon in different reservoirs. We'll see all these different, there's transfers of carbon from one reservoir to another and so on. We'll be learning about these terms today. We actually saw an annual cycle of the carbon dioxide concentrations in the Earth's atmosphere. I like this particular format of the diagram perhaps a little bit better, because what it's actually showing you is how reliable the annual cycle of carbon dioxide concentrations in the Earth's atmosphere are, by showing you each of these curves on here is a particular year's measurements of carbon dioxide. You can see that, you know, some are a little higher and some are a little bit lower, but they actually follow a nice clear pattern every year. And we're going to be focusing in this on the for the first part of this lecture on the land biosphere. We're going to be talking about how the role that the land's biosphere, forests and fields and crops and things like that, jungles and so on, are playing in the maintenance of the carbon cycle. And we'll later move on to oceans and rocks and things like that. Now, the first thing that you see when you look at that diagram that shows the natural carbon cycle is you can see photosynthesis going on. Photosynthesis, of course, is this process that plants use that produces their food. And you do actually need to know, for the purposes of this class, the actual approximate form of the carbon dioxide, the photosynthesis chemical reaction. There's actually quite a chain of chemical reactions that makes this happen, but it can be summarized as a combination of carbon dioxide and water plus sunlight gives a CH2O molecule. This is a building block of carbohydrates like starch and sugar, plus diatomic oxygen. You learned this even in like grade school. You learned that plants use carbon dioxide and water to take sunlight, and they use that to make their food, like starches and sugars, and they produce as a byproduct of that the kind of oxygen that you and I breathe. So plants use the carbon dioxide from the air, they pull the water typically from the soil with their roots, and sunlight to produce the building blocks of carbohydrates plus oxygen. The opposite of that part of the cycle is respiration. This is done by animals, bacteria, also plants do it too, although, we usually tend to think of the plants as doing their photosynthesis. They're actually respiring as well. And again, it's just the opposite of the chemical reaction that we saw for photosynthesis, and you do need to know the chemical reaction, where we're summarizing it as saying that some kind of food from plant material, like sugars and starches, plus O2, which we are breathing in, yields carbon dioxide, water, and energy. The animals are using plant material and oxygen from the air to get back energy for motion and warmth and so on. That's respiration. And the production of a carbohydrate through photosynthesis, followed by its consumption by the process of respiration, produces no net change of either diatomic oxygen or carbon dioxide. This is just a natural cycle that's part of the land biosphere. It only has the net effect of taking sunlight and converting it into a form that animals can use, and all living things can be using for their power, whether that's motion or warmth or whatever. If we're going to be describing this carbon cycle, then using these kinds of terms, one thing we're going to need is a way to describe how much carbon we're talking about. And the book chooses to use the terminology Gigatons of Carbon, or GTC, where it's capital G, little t, big C. G for giga is the prefix we use for giga. T for ton here, and it means a metric ton. A metric ton is 1,000 kilograms. It's a little over 2,000 pounds. And C, big C here being carbon. So we're going to be describing the carbon cycle in this book in terms of gigatons of carbon. But the book does actually kind of make an odd choice here. What they're actually saying, they're actually talking about like the mass or the weight of the carbon atoms themselves. So like in a carbon dioxide molecule, there's carbon, but there's also two oxygen atoms in there. So like if we wanted to describe carbon dioxide in the Earth's atmosphere, a perfectly legitimate way to do it would be to talk about it as like gigatons of carbon dioxide. In fact, there's even a symbol for that, GTCO2. Now, a gigaton of carbon dioxide is not the same thing though as a gigaton of carbon. They both have, of course, the same mass or weight, a gigaton, but a gigaton of carbon is it contains more carbon than a gigaton of carbon dioxide, because the carbon dioxide, a lot of that mass is in the form of the oxygen atoms that are in the carbon dioxide molecules. To keep this simpler, we're going to work in terms of gigatons of carbon. That way we can kind of, recognize, okay, it doesn't really matter. Is it in the form of methane? Is it in the form of carbon dioxide? Whatever, it doesn't really matter. So we're going to describe carbon as it moves through the carbon cycle in terms of gigatons of carbon, recognizing that there are other ways it could have been done. Now, anytime you're in science talking about moving things from one part of a system to another, a terminology that we use is a reservoir. A reservoir is what's a good vocabulary term here? It's where we are storing it at the present time. And so if we're going to be talking about like the land biosphere is a nice reservoir of carbon. There's a lot of carbon in the form of the land biosphere, in the mass of trees, in the bacteria in the soil, in the crops, in the rainforest, in animals. It actually adds up to quite a lot. It adds up to 2,000 gigatons at any given time is the approximate amount of carbon being stored in the land biosphere. How about the atmosphere? The atmosphere is another nice reservoir of carbon because it holds a lot of carbon in the form of carbon dioxide, also in the form of methane, and in fact if we add it all up, the atmosphere as a reservoir has 740 gigatons of carbon in it. Now, what's important here is how carbon can be transferred from the atmosphere into the land biosphere, or from the land biosphere up into the atmosphere. And the unit that we're going to be using to describe the rate at which carbon is moving from one to the other, one reservoir to another, will be gigatons of carbon per year. So we're describing how many gigatons of carbon each year transfer from one reservoir to another. Alright, well there's two important gigatons, two important reservoirs, and so when we're talking about the land biosphere, and so we're going to have two different ways we can transfer it. Not all that surprisingly, they're photosynthesis and respiration. Photosynthesis transfers carbon dioxide, carbon, from the Earth's atmosphere down into the land biosphere at a rate of about 100 gigatons a year. At the same time, respiration by animals, bacteria, plants, etc., is returning about 100 gigatons of carbon per year from the land biosphere up into the atmosphere. And so in the natural world, there's a nice balance here. Now, at any instantaneous time, there's not necessarily a balance at all. In fact, it's actually quite common for there to be some imbalance. We talked about that earlier in the course, about how, in the northern summer, when plants are active, they are actually extracting more carbon dioxide from the Earth's atmosphere than respiration is putting in. So carbon dioxide concentrations fall, and in the winter, when plants are dormant, there is more respiration than photosynthesis, and carbon dioxide concentrations rise. But over the course of the year, the natural carbon cycle between the atmosphere and the land biosphere is pretty much in balance. Now, there's also the ocean. Now, we're not going to get just too bogged down as to how much carbon is being stored in plankton versus fish versus whatever. I mean, we're just going to lump it together and say if it's in the water, it's carbon. Okay, I'm not going to worry about the biosphere versus carbon dioxide that's dissolved into the water, etc. In part because that's really hard to quantify. Okay, we're just going to say once it's below the water, it's part of the ocean. And it's actually pretty easy to get carbon dioxide into the ocean because carbon dioxide is really, really efficient at dissolving into water. When carbon dioxide dissolves into water, it goes through a chemical reaction that produces carbonic acid. Again, you do actually need to know that chemical reaction that I show right there, where you say carbon dioxide plus water produces H2CO3. That's carbonic acid. And you can have the reverse chemical reaction too, where carbon dioxide can come bubbling out of the water in the form of, so from a weak carbonic acid solution and become bubbles of carbon dioxide in water. And again, please do know that chemical reaction. It's also given in your book. This as your book points out, is actually the key chemistry as to how soda works, okay? When you get a can of soda or whatever, it is an acid. It's a fairly moderate acid, but it is carbonic acid because the manufacturer has dissolved carbon dioxide into the water to produce carbonic acid. It's part of what gives soda that sort of tart flavor. But the reason why they do it is because when they open the can of soda, and release some of the pressure, carbon dioxide starts coming out of the water in the form of little bubbles, which is what everybody likes about soda. So adding carbon dioxide to the Earth's atmosphere results in more carbon dioxide dissolving into the oceans, which makes more carbonic acid, which makes the oceans more acidic. In fact, here's a nifty little map that shows how we are experiencing ocean acidification. Ocean acidification is just what it sounds like. The ocean is getting more acidic. Now, you might not remember from like a grade school or high school science class, but the way we measure the acidity of a liquid is using a measure called pH, where smaller values of pH mean more acidic. Higher values of pH mean it's more basic, which is the opposite of acidic. And if you actually look at this map that shows the distribution of ocean acidity or change rather in ocean's acidity, you can see that we have reduced the pH of pretty much every part of the ocean around the world. There are no places where the pH has gone up. Since the Industrial Revolution, the pH of the ocean has fallen by about 0.1. 7 on the pH scale is neutral, so we have reduced it by about 0.1. Paleoclimate records and paleoproxies tell us that the ocean is now more acidic than any time in the last 20 million years. We are definitely changing the acidity as the ocean absorbs more and more carbon dioxide from the Earth's atmosphere. So let's actually talk about how that works. If we kind of think about this again in terms of reservoirs. Again, I showed the atmosphere there as having 740 gigatons. That's the same numbers we had before. I'm not really expecting you to memorize these numbers, but I do want you to have a sense of how big they are and so on. We're going to divide the ocean up into two layers, which I don't know that this diagram here helps very much. The mixed layer is what we talked about, is like where we talk about bulk water temperatures and so on. In your book, they're talking about roughly the top 700 meters or so of the ocean. This is the part of the ocean that can be affected by things like winds and waves and storms and so on. So any kind of motions at the surface of the ocean that can start mixing water from the surface down deeper and taking with it whatever it got from the surface, like heat or carbon dioxide, and bringing it down deeper. We find that then the mixed layer of the Earth's oceans contain about 1,000 gigatons of carbon dioxide. Now, once you get below about 700 meters or so, the ocean down there is not directly affected by what's going on at the surface. You can't mix things that happened at the surface down farther than about 700 meters on any kind of time scale that's relevant to like human activity. The deep ocean, on the other hand, holds, well, I mean, the ocean can be quite deep. I mean, it's miles deep over lots of the depth of the ocean. So not surprisingly, it holds a lot. The volume is so great, so it holds a lot of carbon dioxide. In fact, 38,000 gigatons is the number your book gives. And as we talked about when we talked about transfers of carbon between different reservoirs on land, there's also transfers of carbon dioxide from carbon from one reservoir to another when we're talking about the ocean. At any given time, carbon dioxide is dissolving into the surface of the ocean at a rate of about 100 gigatons of carbon per year. That is about the rate at which the ocean, just by contact with the Earth's atmosphere, is picking up carbon dioxide and dissolving it into the ocean. At the same time, in the natural world, about 100 gigatons of carbon per year bubbles out of the ocean. Not surprisingly, it looks like it's pretty well in balance. But what about the deep ocean? How do we get carbon from the mixed layer down into the deep ocean? Now, it seems to be happening, curiously, at about the same rate, of about 100 gigatons of carbon per year. This is partly just transport by ocean currents that are taking water from near the surface and the carbon dioxide that's in that water and taking it down deeper in the ocean. But it's actually more about organic molecules falling to the bottom of the ocean. This could be dead materials, dead fish, whale poop, okay? Any kind of dead, decaying matter from the mixed layer where most of the fish and stuff are falling down deep towards the bottom of the ocean, sedimenting, to use the right word. That is how we get a lot of that carbon from the mixed layer down deep into the deep ocean. How do we get that carbon back out? I mean, not surprisingly, in the natural world when this is more or less in balance, we have a net transport of about 100 gigatons of carbon up from the deep ocean up into the mixed layer. This is largely done by like upwelling. Along the coast of continents where water wells up from down deep in the ocean and brings this nutrient-rich water where all that slow decay of all that dead material that rained down, sedimented down from the mixed layer down into the deep ocean, when that wells back up along continental shelves and stuff like that, it brings all this nutrients and so on that then revitalizes the mixed layers, the fish and the plankton and all that kind of good stuff. It's why places like off the coast of continents tend to be really good fishing areas where all this upwelling is happening, because there's all these nutrients that then feed the plankton, which feeds the little fish, which feeds the big fish, and so on. Okay, before we start talking a little bit more about these trade-offs and how they affect the exchange with like the geology in terms of rocks and so on, let's run through a few quick questions about what we've seen so far. Here in question 1, which of these reservoirs holds the most total carbon? Now remember, I'm not going to expect you to memorize the actual number. That doesn't seem very helpful. But knowing which of these 3 holds the most carbon sounds useful. The atmosphere, the mixed layer, the deep ocean, or the land biosphere. Alright, make your choice for one of the 4 options below this video and get a little feedback before we move on to question 2.